I will actually stand on this side. Okay. Hello, everyone. And thank you for staying so late. I know it's the last 2 hours of the conference, and I really appreciate everyone being here. So Dawood already talked about natural language data management in the first session of the tutorial. Now I'm going to talk about the second problem. How do we access database through natural language? Just need to put into presentation mode. So first, let me show you an overview of a general system architecture for supporting natural language query to databases. First, we need to have a UI, and a user interact with the UI, issue natural language query. Then there is a component we try to understand the user query and translate that query into a structured query against a data store. So the two optional components, it could have some domain knowledge that we leverage in both query understanding as well as translation. There could also be some feedback generation so that we can get user feedback as needed to improve both the understanding as well as translation. Oh, why it's not working? Is it not working? Okay, let me just use my own. I have another. Oh, actually, this is running out of. This is running out of battery, so this one is not working. No, it's working. Okay, that's fine. I think I will just use a cable. Okay. Can you just plug this back to here and see? Yeah, because I really want to use this thing. No, not working. Okay, that's fine. I will just come back on the phone. Okay. Okay, so we will use more low-tech option. So the first question when you design a natural language query interface to a database is, what is the scope of natural language you want to support? You can support controlled natural language query with, for example, controlled grammar, or you can say I support ad hoc query. Each one of them has its pros and cons. If you support controlled natural language query, it's less likely for the user to make a mistake, but it's more difficult for the user to understand exactly what kind of query you support. If you support ad hoc query, then you put more burden on the system side, because the user can issue any arbitrary query, and it can be very complex. There could be content errors and so on. Those need to be handled by the system in a graceful manner. And also, you may also need to think about ambiguities and passing error, how to handle them in such a case. So the second question you want to think about is, do you want to have a stateful or stateless support for the natural language query? So by stateless, it means that when every query comes in, you handle that query as it is. So the query itself needs to be fully specified and contain all the information needed to answer the query. By stateful, it means that the system is aware of what has been asked before. So when you issue a query, the system can allow you to specify the query in a partial manner and handle the query in respect to what has been already asked before. So think about, you can issue a query like, what is who wrote Gone with the Wind, right? Then the system return an answer, then you can say, what about another book name? So you can ask those kind of follow-up questions. Obviously, it's more natural to have stateful NLQ, but we will see there are also a lot of challenges in doing so. Another thing you want to keep in mind is a lot of time, especially when we look at a paper in the database community, one assumption people often have is parser provide perfect answer, which is not really the case. So we have shown that over news corpora, which is normally most of the NLP tools has been trained upon, the dependency parser is probably about 90%. And this is for English only. If we go to any other language, for example, Chinese or Hindi, it could be much worse. And over question is already worse because remember, a lot of the tools are trained over statement, right? Over news corpora. So questions are typically shorter and with different kind of format. Therefore, the accuracy is even lower. So as I said, the different approaches. One approach is we pretend there is no error, so we ignore it. Or we can say we want to identify certain type of parser error and detect and correct those. Then we can have another approach is identify the error, then allow user to reformulate the query or even correct the parser tree directly. Another major thing with natural language query, as with supporting any type of query as a foreign. One is a vocabulary gap. So when the user issue a query, it may be in a term that is not really exist in the database. For example, if I ask Bill Clinton, right, it's a person name, but in my database, it could be his full name. The same thing with if I ask IBM, in my database, it could be International Business Machine. So how do you identify the gap between the user query and in the database and try to bridge the gap? The second is leaking abstraction. So as we all know, when we design a database, there is a schema associated with it, right? The same when we think about certain things, there are also some way we think of how things should be related to each other, what are the attributes should be associated with different things. And this could be not the same with what the user have in mind and what in the database. For example, if the query says, give me all the top executives in Microsoft, in my database, maybe I do not have a term called top executives. Instead, I have all the person name and their title. And by top executive, I mean person with certain title, like all the person with CEO, CFO, CIO. So how do I answer user query despite of this leaking abstraction problem is another challenge. Then the user query itself can be ambiguous. If I say, tell me more about Watson query, there could be many ways to interpret Watson, right? Obviously, Watson can be a very popular actress, Emma Watson. It can also be a very popular movie character, Dr. Watson, right? So how do we resolve this kind of ambiguity is another challenge. And when we construct a query, after we understand what the user is asking for, and we construct the database query and use that to search against the data store, the construction itself, the different approaches. One is through machine learning. So if you have a large amount of labeled data that giving one user query, and here's the corresponding SQL statement, and you have enough number of examples, there is the possibility of learning the query construction. But the more commonly used approach is construct a formal query using deterministic algorithms. And the target language itself can also vary. So typically, we just use a standard formal query language like SQL or XQuery. But imagine if you want your NLQ be independent of the actual underlying data store, the target language could be an intermediate language that can be run on top of PonyStore, right? So this way, your NLQ is independent of what the actual data store is. So I will show some examples of all of those. So I'm going to cover 8 systems. They are ranging from 2003 to work published last year. So I think this is a good representation of how the database community so far are addressing this problem. And it will illustrate some approaches in addressing some of the challenges. But you are also going to see it actually show you more open challenges rather than the solutions. So the first system is Precise. So Precise is a very interesting system in the sense that it clearly defines something called semantic tractability. I will explain what that definition is, but before I do that, let me first go through the system architecture really quick, and I will dive into each one of them in more details. So the first, it will do dependency parsing, and then it will identify possible parser errors and try to fix it. Then it will try to use the system lexicon to match and type in each one of the tokens and check whether there's equivalent interpretation. And as you can see here, it will involve feedback generation whenever necessary, because there could be ambiguities that the system cannot resolve automatically. Then it will utilize the lexicon to construct the final queries. So semantic tractability defined as follows. First, it defines some term called a database element. Think of in a database, it has a relation, attributes, and a value. So each one of them is considered as one database element. Then giving a sentence, it can be viewed as a sequence of a term. So any term that matches a database element is called a token. And any term that do not match the database element, but matches a predefined set of terms that are going to be called the syntactic marker. So I will show some examples shortly. So a sentence that is considered as semantically tractable will be one where every single term in that sentence is either a token or a semantic marker. And if it's a token, the token needs to match a unique database element. And there are also different type of token, right? So any token matches attribute is called attribute token. So the attribute token should only be associated with a unique value token. And a relation token should attach to either an attribute token or a value token. So for example, you cannot have, let's say a relation token could be written by. You cannot have a sentence called written together because both are actually relation token. So one thing that this work trying to do is recognize certain type of common parser error, especially happening in questions, and try to address them. So there are 2 common errors try to address. One is proposition attachment. The second, proposition ellipsis. So attachment question is saying, for example, here, when we have a parse tree, right? The multiple propositional phrase. Look at the last one. On Monday is a propositional phrase. The question is, what on Monday is modifying, right? So based on the parser output itself, it modifies Chicago. So you're basically saying Chicago on Monday. That does not really make too much sense, right? Because as a city, it does not associate with a temporal attribute. So what the system try to do is try different kind of attachment strategy, try to move up the attachment and say if the current attachment to MP does not make sense. Let's try to attach to its parent. So attach to the parent, but then it's a proposition, right? So we cannot attach a proposition to another proposition. Therefore, this is an invalid attachment as well. So we attach to the next one. So when we attach to the next one, it essentially is modifying flights. So flights on Monday. This makes sense, right? So this is how it changes the original wrong attachment to the correct attachment by iteratively going up in the path tree. So this will fix one type of error called the proposition attachment, which is a very common error in question. The second type of error is when people say in natural language, they can omit the actual proposition. So the two sentences are essentially identical. The only difference is before Monday, there is no proposition on. But somehow we also need to attach Monday to something, right? So Monday right now is viewed as a post-modifier of Chicago. Chicago Monday is not really representing anything meaningful, right? So similarly, what the system try to do is try to remove the current attachment and move up. And to Monday also is not anything correct. So we go up again. And now flight Monday, where Monday as a post-modifier flight to say essentially flight on Monday. That give us the right attribute to modify flights, right? So basically specify a predicate that limit what kind of flight you care about. So these are the two types of error that the precise try to fix. Then once it fixes the path tree, what it try to do next is it pre-builds some lexicon from the database. So as I already told you earlier, right? A sentence, a question can be composed of syntactical marker and tokens. So syntactical markers are something like this kind of propositional phrase, determinator, and so on. Then here are the tokens that actually matches something within the database. So as you can see so here, for example, when we have job token, it matches a table called job, and the term system matches platform. HP matches multiple things. It matches platform. There is a HP platform, and it also can be a company. The same thing here, Unix can matches a platform as well as a job description, and what can matches all of them. So now the next step this system try to do is to use an algorithm called the maximum flow solution, try to assign each one of the token to a unique assignment so that they can maximize the number of different database elements it try to cover. So for job, there's only one thing that it can cover, right? So now it's uniquely covered. And the next one, platform, is also uniquely covered. But when it comes to HP, since we already assigned system to platform, now we can no longer assign HP to platform. So then we assign HP as a company. Then for Unix, we already assigned it to Unix. There is no ambiguity there. And the what going to be, since we already assigned platform and company, we can no longer assign what to these two, right? So therefore, we can only assign what as a description. So by doing this, it allows the system to generate a semantically tractable interpretation and generate particular query where the two predicates were platform equal to SP, company equal to Unix, and from this table, return the description attribute from the table. So even though this system try to address some of the ambiguities, use the maximum flow solution, it may still run into ambiguity issue, right? So for example, when we have systems analyst, the two potential ways to interpret this term. One is the whole thing as a job title, or it can be the area is system and job title is analyst. So both interpretation can be generated as a tractable token, right? Because there are no conflicting between each other. So what the system does, it will give this interpretation back to the user and ask user to say which interpretation is the right one. So as you can see, try to resolve the ambiguities through the building of the domain knowledge, the lexicon, as well as enforcing semantic tractability and asking for user input as necessary. Another interesting thing about this system is that throughout the interpretation, there is no interpretation about the relation. So what it does is it will generate any possible join path between the different element and return all of them. So here I have a very simple database. I only have two tables, job and city, and the join by city ID. Therefore, I only have one particular query, right? Says the platform, I already know, company equal to Unix, they all come from interpretation. But this particular join come from finding this joint path in the original database. But if I have a slightly more complex database where I introduce two more tables, work location and post location. This work location means where is this location for the job. Post location means where is this job is posted, right? Then I will have two different query, and the join path will be different. One joins through the job title to here, and then city ID here. Another one is through this path. So each of the join paths will result in one unique query. Okay, so that's about the precise. I will also give you an overview at the end about all the systems. So next system is called NLP QC. So this particular NLP QC has a pre-processing step involving human. So it generates some lexicon and also patterns from the database, and use WordNet to do synonym expansion and so on. And then a system admin actually look at what it has been generated automatically and curate that to generate a bunch of rule template. So I will give you examples on each one of them. So once the admin set up the system, we can enable a user to ask a natural language query where it goes through the normal question parsing stage, analyzing the semantics using the rule template, and generate interpretation. The template also determines how the question should be translated. The parser used is called a link parser. So now let's go through the pre-processing step. So in the database, it has a table name, attribute name, and so on. Right? We can gather all of those, and the system basically send each of the term to WordNet to obtain corresponding expansion. So it have synonym, hypernym, and so on. It gather all of those. For example, for resource, it has the resource book, volume, record, scripts, and so on. This is already after the system admin goes through what generated automatically through the WordNet. The reason for involving admin here is because if you are familiar with WordNet, you will know every word is associated with different sense. So depends on what's the word sense, the synonym, hypernym, all those things can be different, right? But given the database by itself, it's very difficult to do sense disambiguation. Word sense disambiguation without context is very challenging. So basically, what this system does, it will just generate all the expansion based on all the sense, and then hope the system admin is able to manually curate the generated term. So as you can see here, it will take some effort, but probably not a huge amount of work, depends on how big is your system, right? So once we have this pre-processing step, and there are also some predefined template rules, which I will show you shortly. We just do direct mapping from the path tree node to data schema and the value. So for example, given this particular sentence, what is the author book algorithm? What the system does is just matching using those simple dictionary lookup and find out, okay, what is author corresponding to, what is book corresponding to, what is algorithm corresponding to. So it gives you this initial mapping of the terms onto different database element. Then the system itself contains something called a rule template. It's basically some predicates, if then action that tell us how to mapping it. So for example, this particular says if table author and table resources are used, then and the resource author used, then we should generate this particular query template. So basically purely template based. The challenge here is how do you select the right template to use, and how do you fill in value in the template? So it may not be the only approach you want to use, but the advantage of using template-based approach is if the system do not understand the question, it's easy for you to explain why, because you know exactly what your template is. But the challenge is how do you design all the possible templates, right? So in this system, there is no explicit ambiguity handling. So it's all live up to the original term mapping and the template rules. And also there is no any handling about parser. It's just assume there is no passing error. So as you can see, it's a relatively simplistic system. The reason I want to include this is it includes this interesting template-based approach, which may be useful depends on your application. So the third system I'm going to introduce is called Nanix. It's a more complex system. So as you can see, it has use dependency parsing, and it will classify all the path tree node into different categories. And it also have a way to adapt the path tree onto a new domain, use some domain knowledge. I will give you more example on those. And then validate to say whether this path tree generated can be understood properly by the system. The domain knowledge it use is something built from the XML database to populate the controlled grammar. It also uses WordNet to do some term expansion. This one is interactive and conversational. It actually keeps track of the query history and utilize that information in handling queries. It also be very interactive and have ways to generate message to get feedback from the user. From scope of NLP point of view, it has predefined controlled grammar. This allows the system to be able to tell the user, if I cannot handle your query, what's an example query that may be understandable by the system. So the first step is classification. So it classify when you get a path tree node, for example, here, right, have certain attribute associated with it, like for example, part of speech and so on. We can utilize that within this system to identify tokens, which is a construct in the flower expression, because here we are working with XML. So you try to say if any words that can be mapped into construct in flower expression, including different functions and operators. Then it has the predefined list of marker, different type of marker that cannot be mapped into XML component, but may still be useful. So let's look at the query here. So what are the state that the share water shared with California? So after classification, it tells you what are the tokens. Anything end with T is essentially a token. Anything end with M is a marker. So for example, here, CMT basically tells the system that it understands this corresponding to a return clause. And the state as an NT is mostly likely to be a table name, not a table name, but a attribute name in the XML or element name in the XML. And VT basically means this is a value in the XML. So as I have told you that one interesting thing about this work is it has a domain adaptation aspect, so that it's not limited to what have already been defined by the system. So I will not talk in more details about how to acquire those domain knowledge. You can think of the domain knowledge can be pre-specified or learned through user interaction. As the user rephrase the query, we can use pairs or rephrasing and utilize that to identify potential domain knowledge, right? So imagine, for example, here, if this is my original query and this is my rephrased query, I can take diff between these two trees and use that to incorporate domain knowledge. But here, assuming we already have domain knowledge in advance, and what matches in the domain knowledge is share the water shared width, because this is actually corresponding to a complex semantics, right? So with domain knowledge, we can rewrite the original classified path tree into a path tree that is easier to translate into a query. So it explains to you what share water shared width as the state share a river is the same as a river in California. So essentially, it rewrites the original sentence into one that is more verbose, more difficult for the end user to specify, but easier for the system to handle. But we don't need the user to do that. So by having the domain knowledge, we can issue a query that more database look like, easier for the system to handle. But the user do not need to have the burden to do so. Then the two things I want to mention. One is, let's say my original query, my original term is California, right? But let's say in my database is actually CA. So what this system provided is has term expansion and can replace what in the original query, the term in the original query into a term that is in the database. So instead of California, now we have CA as the value. Then remember, before we do not have state, right? So the system also have some way to identify implicit node and insert into the path tree so that we know, okay, California is actually a state. So this will simplify the job of doing query translation. So the first step of translation is variable bounding. So we talk about all the different tokens, right? Each token, like anything end with T, will be bound with a variable. So we also have variable with star. That means the core token, which will be returned. Because remember, we have this return clause. We need to know what needs to be returned. So the star basically tells us what the variable need to be returned. And the same token, the same variable can happen in multiple places in the original sentence, right? So there is a way that described in the paper in more details about how to assign the same token, the same variable to different token in the path tree, so that we can actually construct a meaningful query. So after the variable bounding, there are deterministic pattern matching rules specified in the system and tell us how to match those variables and its local context into corresponding X-query component. So for example, for each of the variable, it will be associated with a for clause. And any variable that's also attached with I attribute, like I value, going to be put into I where clause, and the join also going to be put into the where clause. So we first construct this fragment, and the next step is how to piece them together. So in this particular example, there is no nesting or grouping. So the piecing them together is fairly simple. We just need to put all of those into the corresponding for clause and into corresponding where clause. So let me show you a more complex example where we need to have nesting and grouping. So in this particular example, we say find all the state whose number of rivers is the same as the number of rivers in California, right? So as you notice, this is aggregation. And since we have aggregation, we will need to do nesting and grouping. So we first go through the same process. We do variable assignment. We create the X-query fragment. And the next step is to identify nesting and grouping. So there's one variable, notice here, called a CV. So C basically means composite variable. It means that unlike those variables like V1, V2, which corresponding to an element in the XML, those variables are created using some aggregation function. So any nesting should be with respect to those composite variables. So I will not go into details about how, like, what's the rule to generate the nesting and grouping, but let me show you the example. So remember, we talk about two composite variable, right? So you can say each one of them corresponding to a subquery in my translated query. So in here, I first describe how to compute number of rivers. So I for every state, return all the rivers from the state. And here for another state and river, return all of them. And then I enforce some predicates for all of them. So for the second pair of river and state, I say the state should be California. And then I compose a join statement, say the count between the number of rivers should be identical. So there is a function here called the MQF. So here we are not translating into a typical X-query. Here we are actually translating into something called the schema-free X-query, so that when we compose the query, we don't need to care about the schema itself. So this simplifies some of the problems, since, for example, how river and state are joined, we don't need to worry about it at the query construction time. Instead, at the query execution time, schema-free X-query is going to handle that particular join path. So one interesting aspect of this work is support follow-up query. So it can detect whether there is any topic switch and say whether I should handle the query as it is, or I should look into what has been asked before and understand the query. So for example, we already asked some query about California, right? Then you can say, what about with Texas? So if we just look at this query itself, it doesn't really tell us too much, right? It just says, what about Texas? But remember, we are asking query within context of what we have asked before. So we already asked, give me all the state whose number of river is the same are the number of rivers in California. So since this is the query context that we have so far, when user asks a partial query, we can assume that this partial query is meant to augment or substitute what already been asked before. So if we look at what could be substituted, it would be just Texas, because all the other things are not mentioned in the new query. The only thing mentioned is the Texas, which is already asked before with a different value. So this system is going to update the query context and replace V4 equal to CA to V4 equal to TX. So this is how it covers the partially matched query. So the way it handles ambiguities are twofold. One is using user feedback. For example, if California has been from the database turned out to be both name or state as well as city, we can ask the user to say whether which one do you mean. In addition, it also leverage schema-free xQuery to find out what's the optimal join path. For example, there could be multiple ways for a river to join to a state. Schema-free xQuery will based on what the actual data looks like in XML to decide what's the optimal join path. And so this system do not handle parser error explicitly, but it does have the interactive UI to encourage the user to input understandable NLQ query. So it would say like, I do not understand your query, but the query I understand looks like follows. So move on to the next system. So this system, the data storage is based on some ontology. And you can see here it actually have multiple parts. So you utilize parsing and then try to do some syntactical mapping. It also try to use the ontology itself to do some direct lookup. So I will explain how these two are done. And in the end, they consolidate both, trying to resolve some ambiguity. So if there are any ambiguity still found, it's going to go back to the user and ask user for clarification. As everything being resolved, it tries to generate Sparkle triple and finally generate a Sparkle query. So because it utilizes both direct ontology lookup as well as path tree mapping, what is this particular system is able to handle is that even if your query is yield form, so even if you are asking keyword query, this system, because ontology-based lookup may still give you some useful information. It may still be able to handle it. But there is no guarantee on when or how it can be handled. So move on to the next slide. So the path tree mapping is based on predefined heuristic rules, which try to find something called a POC, namely potential ontology concepts. It also utilizes ontology itself to do direct ontology lookup and try to find ontology concept. So let me show you some example here. So given the query, what is the highest point of the state bordering Mississippi, it will first try to do a POC, use path tree mapping to identify the highest point, the state, and Mississippi corresponding potential ontology concept. It do not do any type of assignment at this point because potential POCs are just a potential concept. It will do concept assignment later on. But based on ontology itself, it will do some ontology lookup. So for example, the highest point is mapping to property, which is corresponding to geo is has the point of. State is going to map into geo state, which is class, and bordering mapping to another property, and Mississippi mapping to I instance. So after this step, the next step is consolidation. So what does consolidation try to do is look at the span of the mappings between OCs and POCs. So So for example, here the has the point and either has the points of, right, contains the has point. Therefore, we can consolidate these two into the same ontology concept. Same thing here, state the equivalent, we can consolidate. Bordering are equivalent, this is also equivalent. So once we do the consolidation, if there is no conflict, like what we showed in the previous example, there is no conflict. We just move on to the next step. If there's a conflict, then we will go back to the user and ask for user feedback. So for example, given this sentence, return the population of California. So population is not identified as a ontology concept, but California is identified as a instance. So then what the system does is it try to look into the ontology to say, can I find any ontology concept that is somehow similar to the potential ontology concept? And it try to do some ranking based on string similarity and as well as Soundex. So it's a interesting combination of technology. But what it's trying to do is basically look into the ontology to say, what are the potential things that I can use to map population? So this is one way to kind of try to bridge the gap between the user term and what's in the database. But eventually, you also need to ask the user to provide some feedback. So once everything is mapped, what it does is it will try to say, given certain pattern, it will insert something called a joker class, which means just a placeholder. It just gives the name joker, okay? So once we have all this joker class inserted, it tries to generate tuple. So the triples are generated in a pretty easy fashion. We just look at any combination of three things, right? Like for example, joker is a question mark, and the property one mapped here, geostate mapped here, and then the same thing, we map geostate here, property here, and geo Mississippi here. So now we have business different triple. So once we have all the triple, it uses some deterministic algorithm to translate the triples into Sparkle query. So I will not go into details for each one of the Sparkle query, but one thing I want to point out that is quite interesting about this work is, remember we have talked about that there could be mismatches between POC and OC, and the system try to provide some suggestions, right? What it does is, actually, let me first talk about this. Oh, this is not working. Okay, now it actually works. Okay, so it provides suggestions. So as it will observe how the user react to those suggestions and learn a way to improve the ranking method. So this also have some learning aspects in the whole thing, but there's no parser error handling. So let me go back one slide back. So this one I want to mention is because unlike SQL, right, when we compose SQL, you need to explicitly say what to return. But a Sparkle query actually return a graph. But returning a graph to the user may not be exactly meaningful. So this system also try to do some work to try to identify what is the proper answer type and have some UI to decide how to display the result to the user. So it does not just return a subgraph of ontology, but instead it try to group things together so that it can display the results in a more meaningful way. Okay. So the next system is called the Nania. Again, this is also use controlled NLQ based on predefined grammar, and there is no query history. So the system architecture is very similar to the generic one. The main thing that is unique about this is also have some pass tree adjuster. Remember in precise, there's also some way to fix the passing error. The same thing in this system. And in this system, they're also very actively asking feedback from the user. So both at the mapping time as well as at the parser adjusting time, it will generate some message and ask user feedback. So based on some similarity measure to do the mapping, essentially some tree-based, string-based similarity measure. So as you can imagine, this may or may not work, depends on how well the semantic similarity measure works. Then it explicitly asks for user feedback on ambiguous mappings and interpretations. So I just want to show one example about the path tree structure adjusting the path tree structure. So this is imagine this is a path tree structure that directly get out of box. But the system defines some grammar to say what kind of path tree I can handle. So the system is going to look into the path tree returned and try to readjust it so that it become a path tree that can be handled by the system. So for here, for example, it will move the more paper into a different node, and then add the modification of Bob and VRDB as the subtree for more paper. It also then rewrite the original path tree into semantically a more reasonable path tree. So all these rewrite are done deterministic fashion. So there's some rules there to say, given this case, how do I rewrite into a different path tree? So in some sense, you can view this as similar to what we have described before in Nanix, where we have a domain knowledge, and giving a query, we rewrite into a more interpretable tree. Here, it's just done internally. And the translation from the query tree to SQL is one-to-one. So there is no, unlike imprecise, because the interpretation itself already includes the join. So it's going to be one-to-one mapping. So move on to the next one. So this one is actually a fairly simple system. The reason I want to include this is the only system that I can find so far, and it's from the natural language query interface to database point of view that involve some machine learning, not just on the resolving ambiguity side, but actually on the translation side, on understanding the query itself. So use Stanford parser. What it do is it has training data that kind of give you pairs of, so give question, and then what are the mappings of terms in the question into different clauses. And use the conditional random fields to train a classifier and utilize it at the runtime to do the classification. So I will give you more examples about this. Then once everything is classified, it just utilize the ER schema and some deterministic template to do query translation. Because it's doing classification, it do not, even though it's using a parser, it do not have any predefined NLQ grammar. So it just can map arbitrary NLQ query into corresponding attribute mentions. The main limitation comes to the system itself. The system, for example, do not support aggregation, do not support nesting. So the limitation is not very easily commutable to the user. So what I try to identify something called explicit attribute. So explicit attribute are the things that already explicit mentioned in NLQ. So for example, grades and students, they are already in some database element. The database, either the database table or attribute. So those are called explicit attribute. Then in the classification time, you try to classify some of the implicit attributes, actually the values to its corresponding attribute. It will refer to as implicit attribute here. This is actually classified by some third-party classifier. So not the classifier for classifying the type of class. So in the learning part, it only learns how to map those explicit attributes to SQL clauses, basically SQL fragment. So here, for example, those we have list of tokens, right? What are the courses with less than 25 students? Courses is tagged as a group by, and say this is the attribute in the database. And the students also tagged as one. This is an attribute, and it's in the having class. So it defines list of features. Some features can be token based, some are grammar based, some are based on contextual. They have some very specific features defined for this task, like whether this is an attribute, whether any other attribute present, or whether the certain trigger words. For example, each. When you say each or every, this may corresponding to something related to aggregation. So then let's see some examples of how to actually learn the mapping. So this is the example query. What are the professors teaching more than 2 courses? So the classifier going to learn, okay, professor should be mapping to group by, teaching should be mapping to from class, courses should be mapping to having, right? So we already seen the label before. Then once it learn all this mapping, it try to do the following. One is the first step, right? Attribute to class mapping already done by the classifier. The second step is it try to utilize some pattern to identify join based on the ER diagram. So here, since we already have professor and courses from the ER diagram, there's going to be a path that join professor with courses. So that's what this join has been identified. Okay, so another thing is the missing implicit attributes, right? We look at it before. So when you say, when you only have a value like California, there's some third-party classifier used called the concept identifier that can be added back. So there is no passing error handling in this particular system. And also there is no explicit ambiguity handling. No parser error handling, probably not that big deal, because in this system it's just doing classification, right? So the parser output are just features to be utilized by this system. There is no explicit ambiguity handling. So for example, here one length is Mississippi. Here is actually referred to the river, but the concept identifier mistakenly identifies this as state. The system do not do anything, do not come back to us a user to say, is this the right thing or not? It just utilize the concept identifier to do whatever it does. Okay, so this is another system that published recently. So it has controlled NLQ, but it more depends on type of question it can handle. For example, it do not handle why questions. So it's has less to do with complexity of the query itself, but more to do with type of semantics you want to have. Then it also have query verification with feedback. This is treated as it is. So let me first briefly talk about the system architecture, then we can dive into more details. So the first thing it does is to verify whether the query it belongs to the type that the system can handle. If it can handle this type of query, so for example, it may look into some keywords, right? If your query contains Y, then it will be classified as this is a query I cannot handle and just throw an error back to the user. Otherwise, it go to Stanford parser. And in Stanford parser, it does 2 things. It do some pattern matching, try to identify something called information expression. And it also try to do some general query generator, depends on the other system, first system that we just described. So each one of the paths generate different triples. So this IX detector generates Oasis query triple, and the general query generator generates the Sparkle triple. So you try to combine both together to generate the final query. So I will describe each of steps in more detail. So the first thing is the IX actually stands for individual expression. So individual expression can be individual terms convey specific meaning, like it has a predefined list of things, or within the sentence, any reference to the participant or agent that are performing the action. Then it also have some specific syntactical construct in a sentence that it identifies. So for example, given this particular sentence, interesting based on opinion lexicon is identified as a lexical IX because it has a predefined dictionary and it matches this particular term. Then it will identify way as a way visit as a pattern and generalize a corresponding pattern for this textual pattern. Meanwhile, it also processing, so remember it identify all these individual expression, right? Once we identify individual expression, there's a lot of text within the sentence are not handled yet. Because if we come back here, the only two IX has been identified. So only this highlighted has been identified. So the next step is use this system called the FAIR system that we have already described to handle the rest of the sentence. So this system takes the ontology and tell us more about the different terms. So for example, places is identified as an instance of place. The near Forest Hotel Buffalo has been identified as mapping to this particular term near this Forest Hotel, and it also do some standardization, right, in New York. If there's any ambiguity, it's also going to interact with the user to resolve the ambiguity. For example, there could be multiple Buffalo, right? This result, Buffalo, New York, is actually what generated after interacting with the user. In this system, there is no passing error handling. If the query is not fully interpretable, like if the IX and the generic parser handling do not interpret the entire query, then it will just return error. So for those that are fully interpretable, it will generate Sparkle as well as the Oasis query triple, and then merge those triples into a complete Oasis query and search against the Oasis system. So some of the parameters kind of pre-given, for example, limited 5 or support threshold equal to 0.5, those do not come from the original user query, right? So those are the system-given parameters that are used to construct the query. So let me show you one example about how it handles ambiguity using user feedback. Actually, we already visited the example. This is just show that the ambiguity can happen with the larger box because we will not recognize ambiguity until we try to identify the individual expression as well as general query. So the last system I'm going to talk about is called Anthana. So this is a work that I published last year. So what this particular system does is it allows ad hoc query. But again, as most of the systems that we have seen so far that support ad hoc query, it does not really mean that it truly supports ad hoc queries. It only means that when you type in ad hoc queries, it do not immediately give you error message. In fact, there's an implicit limitation in the system that is may be challenging for people to understand. For example, in this particular system, it do not support necessary query with more than one level. It also do not support a certain type of aggregation. So those information are mentioned in the paper, but as the user of the system, may be difficult to understand exactly what this system support. So the overall structure is very standard, right? Remember, we have this query understanding, which is here referred to as the NLQ engine, and then query translation. The domain knowledge utilizes the domain ontology as well as translation index. Translation index are actually built through the values of the database. So remember, we have talked about it. There could be some terminology mismatches, right? For example, if in the system is the IBM, it's an international business machine, and a user query IBM, translation index going to build a certain type of matches between different variants in a database into a translation index so that it can better handle query variations at the runtime. So I will talk more about that. So another thing I want to mention is instead of just return the results, what this system does is also try to come up with some explanation in natural language to tell the user what this SQL statement does, right? Remember, when we provide this kind of system, it does not mean to use by someone who's familiar with SQL already. If you can read a very complex SQL, you probably can already write it, right? So this system trying to, besides just generating SQL, getting the results, also trying to explain to the user, here's my understanding, here's what I translate into, so that the user can understand what the system actually understand. And if there are any ambiguity, the user can better select the right query to go back to the system. So there are several steps within the query understanding. The first step is try to annotate NLQ into evidence. In this particular paper, there is no mention about parsing. It seems to be annotating are based on just a simple dictionary lookup. And the ambiguities are handled based on translation index and domain ontology. So I have some example here that I took from the paper. So for example, this is what potentially in the translation index, or some example. So you can have two kinds of keys from the data value, keys from metadata. So keys from data value, for example, here we have Alibaba, Alibaba Inc., Alibaba Incorporated, Alibaba Holding. Each one of them corresponding to an actual entry in the database. So for example, company.name Alibaba Inc. is the actual entry in the database. But the keys basically show that the user could query this entry using any of those terms, right? You can say Alibaba, and you actually mean Alibaba Incorporated, and you can use the original entry, of course. You can also use more expanded form. The same thing with Alibaba Holding Inc. You can use the original name or partially just Alibaba Holding or just Alibaba. So as you can see here, what it's trying to bridge is what's the user know about a value in the database versus what's the actual value stored in the database. Try to bridge that gap. The same thing for the metadata. So in the ontology, something called personal investment, institutional investment. But as a user, you may not know the differences, right? You may just query investment by an institution, like investment by Warren Buffett versus investment by Alibaba Inc. So the translation that kind of help bridging the gap in the vocabulary, but at the same time, you do not resolve all the ambiguities. So this is the example of the ontology. I'm not going to talk about all of them, but as you can see, it's a graph, right? So therefore, when we try to match in nodes on the graph and we try to create the final query, there could be multiple paths for things to join together. So that's one way of where the final ambiguity can come from. So let's look at an example and see how the system handles this query. So the first step it does is it uses the translation index, try to gather evidence, right? So the two kinds of evidence, whether this is index value or metadata. So restricted stock, it can correspond to multiple index value. It can be holding type, transaction type, institutional investment type. Investments map into multiple nodes in the ontology. It can be personal investment, institutional investment, VC investment. The same thing with Alibaba. We already saw multiple companies can map into Alibaba, right? Since 2012, it's identified by annotator. So it also has some annotator specifically designed to capture time ranges, because time range can be arbitrarily big, right? So we cannot pre-index that. So instead, this actually utilizes an extractor to identify time range expression. And then here is metadata. So once we identify all the possible evidence, then try to match into the ontology graph and see what are the paths that we can potentially join all the different nodes together. So what I have highlighted in bold here is basically what actually could be selected. So here, for example, I can have two interpretation tree where the first part is the same. So we identify institutional investment is a type of investment where the investee is investee company, or it could be in the other tree, it could be security where the security issued by invested company. So in the ontology, there are multiple paths to join the investee and the investee company together. So that's why we have two different interpretation path tree. So once we have the interpretation path tree, this system will utilize some deterministic algorithm to map that path tree into ontology query language. So ontology query language is an intermediate language. So the underlying data store could be relational, it could be graph. So that's going to be handled by the system that is supporting ontology query language. So this is an overview of what current ontology query language support. In some way, you can view it as a simplified version of SQL. So this will greatly reduce the amount of work required by the NLQ system in terms of having to handle the complexity of how the data is actually stored in the corresponding data store. Because then you do not need to worry about the actual, for example, when we store in relational database, we need to make it all the table normalized, right? You don't need to worry about that part. The translation from interpretation tree to OQL is 1-to-1. So we have shown you two interpretation tree, right? So let's briefly look at it here. So for example, for Alibaba, what this particular system does is, although Alibaba actually corresponding to more than one company, this system just union all of them together. So it may or may not make sense, right? Because the user may actually only mean Alibaba Inc., not Alibaba Holding or any other company. But right now, what this system does is just union everything together so that it does not even need to resolve ambiguities at this level. The same thing here. Remember, we have looked at the two different join paths, right? One is the investee and investee company, and the investee security and issued by relationship. So right now, this system just union like both together, just return everything. Again, this may or may not make sense because the user may actually have specific intention on what it means by institutional investment by Alibaba. But what this system does is just decided to union all the ambiguous cases together. And of course, it can also return the corresponding interpretation back to the user. But at least from the paper example point of view, they do not do that. Then once we have OQL, it can be translated into corresponding, for example, if underlying database is SQL, can be translated into corresponding SQL statement and executed there accordingly. So in summary, we have described 8 different systems, and we described the multiple aspects of those systems. So we have talked about scope of natural language query support. So as you can see, most of the system use controlled NLQ, right? Which means that it does not support arbitrary query issued by the user, but instead it has some predefined template or grammar that the system is able to understand and handle. There's some system that is more or less ad hoc, but in reality, it doesn't mean it can handle any query. It only means that there is no error when you type in arbitrary query. It will try to resolve those queries at its best effort, but there is no guarantee that it can actually handle that query. So there's some implicit limitation imposed by each one of the system, but they are not explicitly specified as a grammar. In terms of capability, which means as a system out of box, what it can be support, and after a certain amount of time, whether the system can actually be adapting to the new domain. As we can see, the 2 self-improving aspects related to like 2 of the system, like in Annex, is more about what is the scope of NLQ it can support. In terms of Freya, it's more about how does it improve the suggestion ranking. So in some sense, Nanex, the self-improving aspect is more significant. But most of the system, it just comes with fixed capability. What it can support from day one is what it's going to support 1 year, 2 years from now on. Right? So that's very common. So another thing is in terms of state. So most of the system, except for one, support 1 query at a time, which means every single query needs to be self-contained. You cannot have issue partially specified query. So there is no any kind of conversational style can be supported. So Nanex support conversational style query to a certain extent, but it's also limited in the sense that once the context switch changes, you can never go back. For example, if you ask a query about California, like what's the capital of California, you can say, what about Texas? But now if you start asking what's the longest river in United States, you can no longer go back to say, tell me more about New York State, right? Because then although you're trying to say, I want to also understand capital New York, since the context switch already happened, you can no longer go back. So unlike in a normal conversation, it is possible you have multiple threads of conversation. You can go back some arbitrary point of the time. In Nanex, it's only 1 thread at a time. One follows another. In terms of parsing error handling, most of the systems really do not do anything. So 2 systems try to do some auto correction and some interactive correction, but most of the systems really do not do too much. Because this is also understandable in the sense that parser errors happens in a very undeterministic way, right? So unless you really want to focus on more on the parsing side, maybe for the NLQ system, especially as a academic exploration, you will not really have resources to explore that aspect. For ambiguity handling, most of the system very interestingly try to do it in a more interactive manner. Some systems try to do it more automatically. Some combine both, which I think makes sense because we can probably not resolve everything in one shot, right? But at the same time, you always want to leave the option open to get the input from the user. From query construction point of view, as you have already seen, pretty much all the systems utilize some predefined algorithm to construct the queries, except for this particular case where it uses machine learning to a limited extent. Then in terms of target language, pretty much all the systems utilize SQL. There are some exceptions. But I think the most notable exception is the last one with OQL, which is the intermediate language, which is on top of Polystore. That's probably what we would like to be. Schema-free XQuery kind of interesting as well in the sense that it reduces some of the ambiguities that the NLQ system need to resolve. So now, after I describe all the notable NLQ system so far, and also summarize them, let me try to point out some interesting related area. So one is the semantic parsing. So Dawood briefly talked about it earlier. But what I want to point out is when we look at the NLP literature, when we talk about natural language interface to database, normally they do not really have a database. Normally what they have is some kind of domain knowledge, and then the parsing part is not passing to a database query, but passing to a logic function, for example, into lambda calculus and so on. So in some sense, the semantic parsing in the NLP community is a technology that we can leverage to build a natural language query to database because it understands the original sentence better in the context of some domain schema with some training data, but it do not really translate the original query into an executable database query. So another area that is related is question answering. So if we just look at the system diagram, right, modular some of the small details, you can see they're pretty much almost identical. The main difference is in the query translation for NLQ, for the database domain, it's translating database domain, while for question answering, translating into document search query, and the results returned are actual database records that can be answer user questions. But here is normally a passage that can be used to answer question, and also there's some ranking involved. So here there is no ranking, it's just one answer. Here there could be multiple answers, and then some ranking happens and return that to answer question. But the first component are very similar. So the question and understanding part. Like for example, in question answering, normally people try to understand the intent and so on. In some sense, you can view our way to try to interpret the questions is a way to understand the intent of the original query. Okay, so let's move on to the open challenges. I think maybe Dawood, you can finish this part, and then I can move on to this. Yeah, sure. I can ask. Okay, sure. I think before we go to the last part, since I already talked so much about natural language interface to databases, if you guys have any questions, you can ask it now.
Chicago Saturday. So Saturday cannot be associated with Chicago, so it needs to move out.
Correct.
So how does it know that Chicago is a noun that cannot be associated, and there is this noun can be associated? So it should have a pre-built dictionary, right?
Correct. So it has a. So remember there are database element, right? So when you have Chicago, Monday as together, it cannot find a corresponding database element in the database that matches that. And also Chicago is a location. Chicago do not have an attribute. Do not have an attribute that is a temporal, unlike flight. Flight has an attribute that is temporal. So you can imagine, let's say for simplicity, I have two tables in my database. One is flight, another is the location, right? So in location table, we have Chicago and maybe even state, country, and so on, like city, state, country. So Chicago matching to location dot city, right? But for flight, it will match the table flight, right? Then the Monday going to map into some temporal information. For flight has a temporal attribute called the start date, end date, and in that it will have a date attribute. But in the location, there is no attribute corresponding to the temporal aspect.
Okay. So those tables are just there, they are just collected, or there is some manual intervention in building those tables? Is somebody saying that, okay, for flight, these attributes are valid and I'll store them?
So these are all built automatically because you have a database, right? Yes. Database, it already have a bunch of value there.
Okay.
So you can imagine you can build a dictionary for every attribute in your database and every table in your database. So basically, you can build a three main type of dictionary. One type of dictionary for all the table name, one type of dictionary for all the attribute name, and then one type of dictionary for all the value in the table. Then you can do declare lookup to say what type of element is this. Remember we talked about the semantic tractability, right? So when you're trying to look for Chicago Monday, where Monday is the temporal information and it's a value, it need to modify because both Chicago and Monday are value, right? Value cannot modify value. So every value need to modify some attribute or table.
Okay. Also in the last system, Atana, when you were showing a sentence and you're saying that, okay, this word can be mapped to this. So this mapping.
So these are all based on dictionary. Okay. Just direct dictionary lookup. Think of it as like inverted index for different types.
It looks like even after the dictionary exists, there are challenges in doing this mapping. But how hard is the dictionary building itself? Can it be automated?
Dictionary building can be automated. Depends on what kind of dictionary you're talking about. For example, the dictionary in Precise, the building is relatively simple. It just take the original term and then put into like a dictionary, right? But when we talk about translation index, for example, if you want to say Alibaba Inc. Should be expanded into Alibaba Incorporated, someone need to design an algorithm to do the expansion. So it's also automatic, but some algorithm development need to happen there.
Thanks. Yeah.
Any other questions?
Comments?
So will there be, talking about a lot about natural language queries? Will be some user they ask use their ad hoc queries for say natural language results, query results instead of database query results. For example, if they query for give me the introduction of the most famous person from Illinois. Then maybe in your database you have his birth date, his somehow a little bit about his life stories, attributes. Then how can you construct the natural language results with the database query results to give back to the user? Can we reverse your techniques on understanding the natural language queries to support this constructing natural language results?
Yeah, you can. So if you are saying is how to generate the natural language, right? You can reverse it in the sense that a lot of the work here talk about grammar and template. A very general approach towards natural language text generation through template. And the same thing, when you generate template, you may also have some variance, right? Because you probably don't want to generate the same sentence every single time. So you can utilize some of the technique here that in understanding variance in natural language, in actually generating natural language. For example, when you return the results for international business machine, instead of return international business machine, comma, incorporated, right? You can just return IBM so that it's a more understandable, shorter form of the results, right? The same thing that you can potentially even generate different phrase. For example, we talk about this water shed, right? So instead of saying, return me, here's the river that is the same as the river in California, you can say, this is river share watershed with, or this is the state share watershed with California. So you can utilize reverse engineering some of the techniques so that the query you generate is more natural. Because here we're trying to resolve the problem of user issue a natural query. How do we resolve the ambiguities? I think reverse that is slightly simpler problem. Is also some of the techniques can definitely be applied there.
Have there been systems of papers that enable such functions?
So in natural language processing, there are actually a lot of paper related to this. So the template-based approach is very common. And then people trying to do, like, for example, automatically generating sentence-wise paraphrase or term-wise paraphrase. But it's all still quite limited. Because recently there are also some work on using semantic understanding, something called abstract meaning representation, that we can also leverage here in understanding query for query generation and summarization. So you can definitely look into the techniques that we use here for understanding and try to utilize that in generating text. Okay, I think one last question then.
I have a question about the comparison of these systems. So when you like giving a same sentence, is there a accuracy comparison? Like, for example, a benchmark, which one gives you a more accurate response, things like this?
Yeah, that's actually a very important question, because otherwise the systems are not directly comparable, right? So there are some benchmark data available, most notably called the, I think, geo query, so that's one, and then a couple of other ones. So if you look at the latest, so if you look at the paper here, Anthony, it includes a few benchmark data that you can leverage. But the question for those benchmark data is they are all relatively simplistic. So the database itself is relatively simple. So that means even though a system can perform very well for those benchmark data, in reality, giving a much more complex system, it may not work that well. And also another main challenge is, remember we talked about all the semantic gaps and so on, right? The benchmark query do not include as many variants as what actually happens in practice. And they're all well-formed. So when you actually deploy the system in practice, you're going to encounter many more challenges.
Okay, so to basically summarize what we did and to go over basically again some of the challenges. So what we did is that, again, you look at this as a two-sided coin. I mean, kind of that when you're dealing with natural language text or natural language data, you can treat it as data, and then when you do that, basically the issues that arise is that basically how you store it, how you query it, how you integrate it with your other data sources. So that's kind of one side of the coin, and the other side is that basically you look at natural language as an interface to your database, and that's basically the issues that Yan-Yao covered, like, I mean, that how you can parse your queries, how you can process it, and so on. So again, the first side of the coin, I mean, we treat natural language text as data. Basically, what we did was that we covered, I mean, a number of approaches of querying this. And as you move down here, basically, we are trying to explore more of the grammar, I mean, to some degree. For example, Boolean queries didn't look at the grammar at all. And as you move down a bit, like here, we looked at text pattern queries to some degree, explore maybe grammar a bit. And then also paraphrasing relationship, it does explore more. And then here, like, we work with parse trees. And so again, the idea here is that we wanted to move a bit beyond keyword queries and kind of explore, I mean, kind of what natural language text can offer us. And we also wanted the output to be like, I mean, instead of document, I mean, something that with a smaller granularity. So kind of the idea here is that kind of what, like, I mean, so if you look at it, like maybe compare this to question answering, like, I mean, there is natural language question, and then there is, like, I mean, you pose it into a repository, and then you get basically some answers. The idea here is that instead of natural language question, maybe we can use some queries that maybe it is easier to understand, easier to parse, but kind of it will be useful, I mean, when you want to query the data and then perhaps integrate with other sources. Okay, so some of the challenges is that, again, maybe, like, I mean, again, looking at the grammar, I mean, kind of if you want to really, like, query natural language text, we need to understand grammar. We need to use grammar, or we need to be aware of grammar. Some of the challenges are like queries without knowing the schema. I mean, kind of if you can treat the grammar as a schema, often we don't know the schema, even though we have maybe like a general understanding of how schema or grammar is going to look like in English, perhaps. Again, if we treat grammar as a schema, like, I mean, you have many table schemes, and there are different forms of relationships between these schemes. For example, some of them are going to overlap, some of them are going to be equivalent. I mean, kind of, we saw some examples, like, I mean, there are different ways of saying the same thing. And then it kind of, again, if you look at each one as a schema, basically these schemas are perhaps equivalent. There are some promising development. I mean, kind of, there is, like, I mean, say, work on paraphrasing relationship between text phrases, tree patterns, DCS trees, and so on. And those are the kind of resources that we can tap into. And then there are also developments of resources and shallow semantic parsers and so on. Basically, again, those are the resources that we can look into. So one issue, again, another like development or another direction is like that basically, this was one of the systems that, like, this white table that we looked at, one of the papers that basically it described, like, I mean, text as like each document as a tuple. And as you explore document, I mean, kind of you end up adding attributes to this table. So kind of something like this, I mean, maybe like, I mean, an approach like that, that is important, I mean, in here, that basically, as we explore text more, we are finding some of these things, and basically later on, when we come back to the document, we have explored already some of these relationships, and we are building on top of that. So the more we work with these documents, I mean, kind of, we are gathering this information, and then kind of the system kind of improves itself. Okay, so we also covered basically integrating and transforming natural language text. So again, something that I can do is that I can take natural language text and I can transform it into a format that basically I can easily query, and perhaps I can integrate with my other sources like relational data. So we talked a bit like some work on transformations on text and integration, loose and tight integration. in the database community, there is more work on loose integration and optimizing query plans, and perhaps we need more work, I mean, kind of on tight integration. Again, some of the challenges here, like, I mean, all the challenges that you have to deal with when you want to understand the semantics. I mean, kind of those challenges are there, but other communities are working despite those challenges. I mean, kind of like, I mean, we are seeing progress in many different fronts. For example, work on transforming text. I mean, we see progress in this area. The resources, we are developing more resources, and those resources help us basically understand semantics better. We are making progress, or perhaps other communities are making progress in shallow semantic parsing and other areas, and we see progress in areas like, I mean, translation is speech recognition. The reason I have it here, it is because those are I mean, kind of inspiring in a sense that maybe 20, 30 years ago, if you talked about, like, I mean, that how good the translation can come along, or how good the speech recognition can come along, I mean, kind of, there wasn't, like, I mean, you didn't get a promising answer. But now that you look at, like, some of these tools, again, they are not perfect, they have error, but still, I mean, kind of, we have come a long way. And perhaps one of the reasons is that some of the resources that become available. So the idea here is that, again, with these resources, with the kind of progress we see, I mean, here, there are basically demand. There is a big demand, like, I mean, to store, I mean, kind of this data, and then, like, to use it or to query it. To give you an example, for example, Stanford parser. I mean, like, how much this thing is used. I mean, kind of, you look at, like, many papers, many systems use something like this. Okay, so we in the database community, perhaps we can provide some tools to store, I mean, kind of the data, and then kind of retrieve it more efficiently. And if we can build some of these tools and building blocks, I mean, kind of, this can be used by large number of communities, and those are the areas that perhaps we can contribute. So basically, if you can build a tool that is relevant, I mean, kind of, there is going to be lots of demand. I mean, kind of, so those are the areas that perhaps, like, we can contribute. There is structure in natural language text, then just text as a sequence of tokens, and those are the things that I mean, as we are building tools, and we need to be aware of that. Looking at some of the transformations that basically people do on natural language text, one of the papers that I reviewed, to do the transformation, for example, they do in one particular data set, they end up sending 600,000 Sparkle queries to a data store. So to me, like, that provides an interesting opportunity for us, I mean, kind of understanding the kind of queries that they are sending, and then perhaps what we as a database community can do, I mean, kind of, to better support those queries. So those are the areas that we can basically contribute. And some of the things some of the things on, like, I mean, on reasoning, and the kind of, once you do the mapping, I mean, what kind of things you can do is that, again, this is an area that database community has done quite, I mean, a large volume of work. I mean, kind of, the question now is that, can we apply some of those, I mean, kind of, to these basically new challenges, and what are the issues that we can tackle?
Okay, so let's visit what the ideal natural language interface to our database should be look like. Ideally, it should support any queries that we would like to ask, right? It should be improving as we interact with the system. It should be getting smarter with time. And it should be conversational, just like when we interact with people. Imagine when you watch Star Wars, right? Maybe you want to have your own R2D2 for your database. We want to have a conversational interface. And ideally, there should not be partial error. And if there are any, it should be automatically corrected. But let's look at what's the reality, right? Reality is far from there. So these are all the opportunities that we can really think about. How do we work so that we can make our dream closer to reality? So for example, here, when we support ad hoc query, if we cannot completely be ad hoc, even if we have controlled query, how do we convey the limitation to the user? And how do we support when the query out of scope in a more graceful manner? For instance, can we somehow degrade to how IR community handle keyword query if there's query we cannot handle, right? They are all possibilities. And the self-improving part, as you have seen, really, we're not leveraging learning here too much. Well, similarly, when we look at IR community, right, they look a lot in query reformulation. Can we borrow something there to improve natural language query interface? And can we make the natural language query interface more interactive? So as you can see, even with simple technique from Linux, it can already be much more interactive than all the other systems, right? So I think the conversational part is definitely going to be something very interesting. So one work I did not cover intentionally in this work is I recently cited a paper about a chatbot. So that chatbot really borrowed a lot of ideas from Linux in terms of interaction style. The reason I didn't include it because it's not really accessing database, but more of creating programming. But these are the kind of things you may want to look into if you are looking for your next research project. How do we build a chatbot against the database? And when we handle passing error, even if we cannot handle it completely, maybe for the common types, like what the precise is doing, right? For the common types, can we have some way to address them? Looking at other aspect, right? Ambiguity handling. Ideally, we want to do it automatically. And for query construction, ideally, we want to start with some deterministic rules so that the NLQ, the natural language interface work out of box. And then as time goes along, we want to use machine learning to make it smarter. As we're getting more training data, we want to learn how to handle some of the corner cases that are not covered in the original rule-based system, right? And the target language, when we all talk about polystore here, can we, when we design the next natural language interface, taking a polystore language as a target language so that we don't need to worry about moving from one system to another. So the reality is far from there, but there's hope, right? So we already make a long way in the rule-based system, and combine the rule-based system with machine learning approach can be an interesting aspect. And in the ambiguity handling, there also a lot of work has been done. That definitely many more work can be done here. So in this conference, right, we have seen a lot of work on entity resolution, which handles how to resolve the mismatches between different structured data. In my view, to a certain extent, right, at least for the terminology aspect, this has no difference. It just happens dynamically. When you're in your query, you're looking for something, some specific entity that's already in the database. How do you resolve that entity mentioned in the user query to the things in the database? So there are lots of work that we can borrow from entity resolution and to improve this aspect in ambiguity handling. So there are many open challenges. So we look at this diagram before. I make it slightly different in the sense that in the end, we also want to leverage the text document as well in our data store. But let's look at all the different challenges, right? So how do we support ad hoc NLQ query with complex semantics? We don't want to just support keyword queries, selection queries. If we do not support aggregation, we do not support complex selective predicates, then what's the point of using database, right? And we want to handle parser error better. We want to bridge the terminology gaps, automatically identify, resolve ambiguities, and more importantly, because of the current limitation, if we cannot do everything automatically, involve human at the right moment, so that we do not just pretend we can do everything. Let's work together with human in the loop to have the task done. Another aspect that none of the system try to resolve today is how to do it for other languages. There are over 3,000 languages in the world, right? Right now, most of the work, pretty much all the work I have seen, really focus on English only. So when we move on to other languages, there may be additional challenges. I don't know, but definitely this is something we would like to have. Then right now, the domain knowledge requires either some programming aspect or automatically, but with human involvement. Remember, we have talked about when we do automatic synonym expansion based on WordNet. Someone needs to go through that list and see what's the appropriate, right? We don't want human to be in that loop always. So how do we construct the domain knowledge to help natural language interface resolve ambiguities better is another important aspect. And right now, most of the systems, the type of queries can handle are relatively simple, not exactly what a human expert would be able to construct. So some of the challenges need to come from the query translation side. Then from the data store, as I already mentioned, right, we want to support a polystore. We want to combine structured data together with unstructured and semi-structured data. Because even though there's a lot of effort today in building knowledge base, you can imagine that no matter how much effort you put into building knowledge base, there's always going to be information available elsewhere, not exactly knowledge base, right? So how do we, before we have a complete and perfect knowledge base, how do we allow user to actually access information already reside in the non-structured form? And finally, the feedback generation is another important aspect, because even as a human, right, when we talk to other people, when people ask you a question, you may not always be able to give a perfect answer in one shot. You may need to clarify to say, what do you mean by this question, so that you can get a better answer. The same thing here with any computer system. You want to give the human opportunity to provide input. So that's a very important aspect, right? How do we engage human? How do we let the user understand and be able to work around any limitation we have? And also right now, I'm also only talking about natural language interface. But in reality, we interact in different form, right? A famous saying is, I picture words 1,000 words. Right? Sometimes we may want to say, I want to search this with image, then I can ask follow-up questions with the natural language. Right? Since we have multimodal database, then we should also support multimodal interaction to a certain extent. Finally, the system should be self-improving. It should getting better always, and maybe have some kind of personalization. So for example, if I'm the store manager of Walmart in San Jose, when I ask, what's the best selling product in my store, you better be able to know who I am to give me the right answer, right? And be conversational. I already said that conversational is important. That's how people interact with each other. If we really want the interaction to be natural, we want a system that is conversational. So here in the audience, most of us come with database background, right? But I want to point out, to solve all the problems that Dawood and we have talked about, database is just one piece of the puzzle. We need to put together all the pieces together to really solve the puzzle. So natural language processing, no question, right? We need to utilize technologies happening there to understand text better. And we have to have human-computer interaction so we can effectively communicate with the user so that we can work together. We're not working for each other, we're working together. Then finally, how do we leverage all the advancement happening in machine learning to improve all the problems that we have talked about, all the solutions, right? So I hope this gives you a very good idea in terms of if you are interested in doing any research related to natural language data management or natural language interface to database, what are the additional things or field you can look into to find the inspiration or tools to improve your system. Thank you. I think we still have a few questions, like few minutes to take questions. If anyone want to ask questions, we can take additional questions.
How do you think, how important are the NLP parsing techniques in this context? Because when you look at other data like tweets and stuff like that, you have way more unstructured text, and all these parsers might not work as well on tweets and so forth. So do you think there should be other approaches as well, aside from trees?
So in natural language processing, there are actually specific research area on handling noisy data. For example, for tweets, depending on what you want to do, one way to do it is you can train normalizer, again, a tool from natural language processing, normalize tweets so that the Twitter messages become cleaner English. Then you can leverage the standard tools and be able to do the typical data management as it is. So definitely, we need to put together all the different pieces. Depends on the specific scenario, some pieces may be more important than the other. But since all the field kind of moving forward, right? So while we're working on resolving some problem related to database, we need to look into what is happening for the other area.
Again, one comment related to this one is that, again, because of the amount of resources that, the amount of resources that we are getting, for example, we have more tweets and we have more annotated data that basically we are gathering, and then it kind of, as we are moving forward with the amount of data that we are collecting, I mean, it allows us to build, I mean, kind of tools or machine learning algorithms that basically kind of to learn from, I mean, kind of with what we have and that we know, and then it kind of given a short text, I mean, perhaps interpret that better, I mean, kind of have a better understanding of those short texts.
Yeah. So another thing I want to mention is I myself come with database background, but right now I'm actually managing a team called a Scalable Natural Language Processing. So what we do there is we take a database approach, solving the natural language processing problems. Because in natural language processing community, typically they don't care about things that we care as a database community, right? Here we care about scalability, we care about how do we handle large scales, right? In typical traditional NLP research, they don't care about those things. So another opportunity, kind of somewhat related to what we have been talking about, but it is also slightly independent, is how do we take our database approach to solve some of the problems in the other area? Because in the end, we have to put all these puzzles together, right? So if we cannot do NLP at a scale, then I cannot have the hope to managing all this natural data at a scale, because we have to use those tools. So that's another direction you can look into. What are the tools that we need to use from this area that do not satisfy the kind of requirement you have, right?
So you use the word polystore in one of in a few slides. What do you mean by that? Does that are you talking about independence of the type of text that you're querying from? Unstructured
Which term are you?
polystore? Polystore.
Oh, polystore.
Yeah.
Polystore is a term that I think getting coined from last year. So like many researchers from MIT and University of Massachusetts, Amherst, like a bunch of professors and also Brown, kind of talking about, right now we have relational store, we have graph store, we have like, for example, inverted index type of thing, right? So now the store can satisfy all the data management problem that we have. So the pollen store kind of trying to say, let's put all the different type of stores under the same umbrella, design one unified language, and channel the corresponding query to the right store as needed. So you can look at the last paper, the answer paper. It also talk about the pollen store. So you can, from there, you can look at some citations. Yeah, but the idea is for instance, when we trying to integrate natural language data with structured data, right? We cannot have the hope store everything in natural language into relational store. So when we do that integration, it already become pollen store. Okay. Okay. Thanks very much, everyone. Have a nice trip back home.